Hello everyone, welcome to our lecture on derivatives of exponential and logarithmic functions. What I have here is a list of all the formulas, the derivatives of functions, and I want to just quickly run over them one by one. Now, we're looking at them in specific and general categories. So we're going to specifically look at natural exponential function, right? Natural exponential is E. And we're going to look at natural log function, and then we will open it up for general exponential and logarithmic functions. Okay. So the derivative of e power x, good news, is e power x itself. Okay. So if you had e power x, it comes back as e power x. If I had something else to the e, if I had something like, let's call it u, okay, but you're deriving with respect to x. If the variables do not match, right? Exactly, it has to be exactly an x. If it's x squared or 2x or 5x plus 3 or whatever, something else to it, or 1 over x or something that's different from an exact x, then what it says is we have to use the chain rule. So we need to take the derivative of e, which is e itself, with the same u. So that's derivative of e times the derivative of that u. Okay, that's the form that they've given us here. They're saying, well, if this u was some function of x, so let u be g of x. So just remember this, okay? If it's exactly x, derivative of e power x is e power x. If it's something other than x, but it's a function of x, but it's not just a plain x, then you'll have to do the e power u's derivative, which is itself e power u, but then you'll have to also take the chain rule, which is the derivative of this u. Okay, so the chain rule kicks in when you have a different expression other than x. Let's come over here. For natural log, the derivative, right? The derivative of a natural log is 1 over x. Let's just write that here. Okay. D over dx of ln x, natural log of x, is 1 over x. Okay, so this x and this x are exact. They're identical. Okay, if you had something else in addition to that x, like an x squared or 1 over x or 2x plus 5, anything else, I'm going to call it u. Then we're saying, yes, you'll have to still use this 1 over u, right, whatever that function is, times the derivative of u. Okay. Now, once again, u is a function of x. Quick comparison. And a natural log is the inverse of natural exponential expression, right? So we have e power x, e power u, both condition discussed here, where e power x is the straightforward differentiation. E power u involves chain rule. Likewise, the natural log, directly x involves 1 over x. If it has something other than x, then you have the chain rule that kicks in. What about this? Now this one here, general exponential logarithms. Now for the exponential and logarithms, we are not looking at, of course, the natural exponents or the natural log. Therefore, we're looking at any log with a base b. Okay. So again, a quick side discussion on that would be derivative of log x to the base b. The x's match, right? Exactly. It's going to be 1 over x natural log of b. We convert all these to natural log because we don't have to then deal with the base. Right? And then we're saying if you had something else other than the x, then we have 1 over u ln b, right, whatever that base is, times derivative of that u. Yeah, look at here. So that there also we had derivative of u, just the u, and likewise times the derivative of just the u. Okay. And for exponential, notice that we're looking at b power x, not e power x, because e power x was a specific case we discussed already. And so we now have similar expectation. Maybe I'll just write it down here. D over dx, b power x is b power x ln b, natural log of b. And if we had something else as b power u, the variables don't match, but u is a function of x, then we have b power u ln b times the derivative of u. Okay. They've used the g of x notation, so it looks slightly different, but it's all the same. And they also use the prime notation. We use the d notation, d over dx notation. So just for variety, just for more clarity, I like to present it like this. Okay. All right, so those are all our formulas, and we're going to use them in our computation for finding the derivative of any of these exponential or logarithmic functions. Now let's say we're asked to find the derivative of f of x equals e power tan 2x. Okay. Now I want you to pay attention to this part. Okay. This is like your u, because it's not a direct x, it's not a plain x. So u will be tan 2x. Okay. So keeping that in mind, you are then trying to find f prime. Let me write that down here. F prime of x is what we're trying to find, the derivative, right? Which is, again, for variety, I'm using the d notation. You're trying to find the derivative of this e power u, right? I'm calling this as u because it's something else than x. We know that the definition for derivative of e power u is e power u itself times derivative of that u. Agreed? Let's go back to check that. That was the very first thing we did, right? Derivative of u is an additional 1 to the e power u. So let's come down here. All right. So e power u is e power tan 2x. So that's straightforward. Now we need to find the derivative of this u. So we come back here and we say, what is du over dx? The derivative of u with respect to x is, you need to find the derivative of tan. Well, the derivative of tan is secant squared x. But remember, here again, you don't have a plain x. You have something else. So remember, if it is not a plain x, chain rule kicks in. So the chain rule says derivative of the outside times derivative of the inside. So this is a double layer chain rule. So we now have derivative of the outside, which is secant squared 2x, because the derivative of the outside was only the focus on tan, times the derivative of the inside. So let's take a quick shot at what we just did. Derivative of, oops, that was the outside. The outside was tan. So tan's derivative is secant squared. And the derivative of inside is the 2x. Okay. So let's clean that up. Derivative of 2x is 2. So I'm going to write that as 2 secant squared 2x. Agreed? And that is what I'm going to bring out here into this step, because the step is asking us to find the derivative of u with respect to x. And we got that to be 2 secant squared 2x. You can technically leave it like that, but a little cleanup means that you put the 2 in the front so it doesn't get lost. And secant squared 2x. Please put those parentheses around so we know that they are grouped together for the argument. Okay. And that is your answer for this problem. Well, this problem helped us to see that we were doing multiple things here, right? We used the derivative of exponential function, then we used the derivative of a trigonometric function tangent, and then we used the chain rule also on top of that. So we're going to do a similar problem. Find the derivative of y equals e power x squared over x. Okay, it's kind of stacked up there. Got that. Well. Now you have e, but that e is sitting in a fraction. So you need to find y prime, which is to take the derivative with respect to x for this expression. So when you write it like this, it kind of pushes you to realize that to do the derivative, because it's in a fraction form, we have to use the quotient rule. Okay, so you need u, the numerator is your u, and your denominator is your v. Okay, you need to find u prime, and then you need to find v prime. V prime is very simple, it's just 1. But u prime, you notice that this is not a plain x, right? It's got x squared actually. So the rule tells us, the exponential derivative rule tells us that we need to take the derivative of the e, thankfully it is the same, so e power x squared itself, times derivative of that power, right? Because the power was not a plain x. So derivative of x squared will be 2x. So notice how we did use the rule of exponents within the quotient rule. We're going to utilize the rule itself, the quotient rule itself, which says u prime v minus v prime u all over v squared. So let's come over here and apply what we have. So this is 2x e power x squared. So u prime v minus v prime, which is 1, times u e x squared all over v squared, which is x squared. Okay. So we are technically done with applying the quotient rule. Now we need to clean up. And so I have an x here, I have x here. So that's going to be 2x squared e power x squared minus e power x squared all over x squared. E power x squared seems to be common to the terms on the top. So that leaves us with 2x squared minus 1 over x squared. You really can't simplify any more than that. So this is the simplified form. Don't be tempted to cancel off this x squared with this x squared in the power. Okay, the e carries the power x squared, so you cannot cancel the x squared by ignoring that e. All right, so that was our answer for y prime, the derivative for the given function. Okay. Now let's take an example under maybe logarithms. Find the derivative of f of x equals natural log of x cubed plus 3x minus 4. Okay. So we're now looking at the derivative of natural log. So you can go back quickly to our formulas that specifies the rules for natural log. So we have come over here. If it's a plain x, it's 1 over x. If it is a u, it's 1 over that u, whatever is here, it's 1 over that, times the derivative of that u. Okay. So clearly we do not have a plain x. We are not given ln x, we're given ln, a huge expression in x. Okay. So we come over here. and I'm going to call this whole thing as u. U equals x cubed plus 3x minus 4. I need to call it that because I know I have to take the derivative. So du over dx will be 3x squared plus 3. Let's come over here then. F prime of x is the derivative of this ln x cubed plus 3x minus 4. Okay. And we just call that huge expression as u. So it's ln u. And the rule says the formula then is going to be 1 over u times du over dx, derivative of that u. Okay. So we just found du over dx. So all we have to do is now write this u. U is that x cubed plus 3x minus 4. That's the whole u times, we just took the derivative of u, that's 3x squared plus 3. Always remember that this is happening in the numerator. If it's confusing, drop a 1 underneath it so that when you combine them, you can shove them in their corresponding positions. Minus 4. Once again, do not go beyond what algebra allows. So don't just cancel off the 3's or the x's and all that. You can factor out a 3, but it doesn't lead us to anything simpler, or doesn't help us cross-cancel or simplify the expressions. And so we just leave it right there. Let's check out another problem. Find the derivative of f of x equals natural log of x squared sine x all over 2x plus 1. Okay, this is a classic example where we can actually use algebra. Remember algebra before calculus, right? So you can use algebra to simplify it and then apply calculus. And so what we're doing here now is going to see if we can apply the properties of logarithm. Okay, and that's coming from algebra. So the quotient property tells us that if you had natural log of something over a natural log of a quotient, then you take the natural log of the numerator minus natural log of the denominator. Okay, and here in the numerator, so this was the quotient rule. We have this name for almost everything. So this is quotient rule of logarithms, right? Not for derivatives. Then we have within that, we now have product rule, because there's product happening, rule of logarithms. So product rule of logarithms says, well, you can add them as individual logarithms. So that's going to be natural log of x squared plus natural log of sine x minus the second expression, which was 2x plus 1. You can't separate that. Don't try to distribute the logarithm and all that. Okay, that will be problematic. This was on the left, it was still f of x, because we are still doing algebra. We're not doing the derivative yet. Now we're ready to do the derivative. So derivative of this. Now once again, it's natural log of not just a plain x, but x squared. So the rule says, write it as 1 over whatever is in the argument times the derivative of that. That's going to be 2x. Plus, here too, it's natural log of sine x. Sine x is not a plain x. So we just have to do 1 over sine x times derivative of sine x is cosine x. Got that? Minus. Here too, it's not a plain x. It's got an expression there. So it's 1 over 2x plus 1 times derivative of this expression. Derivative of 2x plus 1 is 2. All right, then we've got to simplify these things. So that becomes 2 over x plus, this is cosine over sine, so you can simply write it as cotangent x minus 2 over 2x plus 1. And that's the answer. Then here's our next problem. Find the derivative of h of x equals 3 power x over 3 power x plus 2. Okay. So it's got a different base. The base is not an e anymore. The base is now a different b. In this case, it's 3. So as you inspect this, you're trying to find h prime of x, which is taking the derivative of this expression. Again, as soon as you write it like this, you know you've got to use the quotient rule of derivatives. So the numerator, you're going to call it 3 power x. The denominator, you're going to call it 3 power x plus 2. And you need to take the derivative of that. So this is b power x format. So let's go to our formula list. And our formula list now would be applicable for the general exponential properties. And then we have 1, 2 variations. So the first one was for logarithm. The second one was for b. Right? So let's just come over here. So it was b power x. B could be any number, right? So b power x. In our case, it was 3 power x. So 3 power x. So then we're going to, if you use the formula, you'll replace all your b's with the 3's. So it's going to be 3 power x, ln 3. I'm going to come down here and utilize that. So that's going to be 3 power x, natural log of 3. V prime, interestingly, V prime also would be just this term to be derived because that's the only one with x. That also will be 3 power x, ln 3. Now this is the quotient rule. If it helps, always write the rule. Okay, now we have u prime v minus v prime u all over v squared. So that's going to be 3 power x plus 2. That's getting squared. Okay. Now remember to distribute this whole thing to each term here. So that's 3 power x times 3 power x. Okay. So you add the powers. 3 power 2x ln 3 plus 2 times 3 power, hold on. That looks like 23, right? So 2 times 3 power x ln 3. Typically, we put the ln also in the front. Okay. Minus. This is going to be 3, once again, 3 power x times 3 power x, so 3 power 2x ln 3 all over 3 power x plus 2, the whole squared. What's really cool about this is that these two are equal and opposite, right? The same, one is plus, one is minus, so they will cancel off, leaving us with 2, let me put 2 ln 3 times 3 power x, just for, because there's no really rule to say which goes in front. It's just that I'm putting, these are all numbers, right? 2 and the ln 3, they're all going to be numerical answers. They don't have an x in them. And so I put them in the front. That's all I tried to do. Whole squared. So this one involved quotient rule, and within quotient rule, we use the exponential derivative rules. Hope this was helpful, and just try to explore more examples. You'll see different types for different homework sets, and with more practice, you'll be able to flexibly utilize combination of rules and stack those rules wherever needed, because mostly it'll be nested one inside the other, like a chain rule will be nested inside a quotient rule, which in turn is nested inside an exponential rule. All right, thank you, class.